Hello everyone, my name is Mo Huiyu, a PhD student from Tsinghua University. I feel very honored to be here to present our team's work. Our team's work is about an energy-efficient engine to compress and accelerate convolutional neural networks based on transfer filter-based algorithms. My presentation will proceed as the following contents. The first, why we should compress and accelerate CNNs. Nowadays, mainstream CNNs are formed of different kinds of common layers and fully connected layers. In this way, billions of marks and parameters are required. This is intolerable for many platforms, especially for power intensity platforms such as embedded platforms. So to tackle these problems, many great works have been proposed. For example, some works focus on reducing marks, like the prediction-based works. They focus on reducing unimportant marks, like when the ground-based works. When the ground-based works is to change the computation flow to reducing the marks. However, the mode compression are not considered in these methods, namely the parameters are just kept the same. Also, some methods like the prediction-based works may sacrifice higher accuracy. On the other hand, many works focus on making use of the sparsity of CNNs. Yes, high parameter reduction ratio have been achieved in these methods. However, irregular computation in the CNNs cause higher power overhead and not that high speed up. These two problems have not been completely addressed, so we considered to use transfer filter-based algorithms to address these problems. So what's the transfer filter-based algorithms? In the world, there are four main transfer filter-based algorithms. In the world, these transfer filter-based algorithms mainly explore the attributes of the kernels of CNNs. For example, like the translation attributes, the rotation and the symmetry attributes, and the negative and positive attributes, and the bias attributes, and so on. They also can achieve higher parameter reduction ratio, but also they have much regular computation flow than the sparsity-based algorithms. However, there are many redundant computations in this algorithm that are not considered by these algorithms. Let me take the DCN and SCN as an example. Let's look at this. The one entire weights of different kernels are just the same, like this row and this row, and in CNN, the 3 rows and these 3 rows are just the same. The difference is that their locations are different and they are symmetric. And on the other hand, in the one row weights, there are also repetitive weights. For example, in the metafilter in the DCN, there are two kernels. There are two kernels that have the same weights, like the weight 1 and weight 2 in the TF1. Weight 1 and weight 2 also are in the TF2. So in their common process, let's look at this picture. When they are processed with the same input activations, there will be some products and p-sums. These products and p-sums will be recomputed. Also, this is similar to the SCN, and like this, the TF1 and TF2 are symmetric, and the products and the p-sums will be recomputed too. So If we can eliminate these redundant marks, a higher acceleration can be achieved and with the model completion ratio unchanged. So we propose our own architecture named TFE. So first, please let me introduce the overall process of the TFE. Given a CNN model, this model will be trained and transferred in the training process, and then our TFE will eliminate the redundant computations, and then we proposed a hardware architecture to support the above process efficiently. Our TFE hardware architecture is mainly formed of three modules: the memory system and the P area. The P area consists of 2056 PEs and a stacked register group. The stacked register group its function will be introduced in the following situations. So now, please let me introduce the three contributions of our architecture. The first, we should to eliminate the redundant computations in the one row. So let me take the DCN as an example. There are two original curves in the one metal filter. Like the TF1, the weight 0 to weight 2 is the TF1, and the weight 1 to the weight 3 is the TF2. So in our comp process, when the first activation is input, it will be multiplied with the always, and the product will be stored in the stacked register. And with the second activation is input, also the product will be stored in the stacked register, and these products will be added with the form products like this, and generate the p-sums and stored in the register. And when the third activation is input, also the products will be stored, and the products will be added with the form 2 p-sums like this. The products will this product will be added with this product and the p-sums, and generate the two new p-sums. For 1 times 3 count process, this p-sum and this p-sum will be output for the two output future maps. And when the fourth activation is input, also the product will be stored, and they will be added with the form 2 p-sums and the products, and to generate the new p-sums. And at this cycle, another 2 p-sums will be output for the two output future maps. In this way, the products and the p-sums will be reused for different output future maps, and the redundant computation can be eliminated. It's also the same. It's also the same for the SNN. The products and the p-sums will be reused for the different output future maps. And the second, when we have eliminated the redundant computations in the same row, we should focus on eliminating the redundant computation among different rows. Let's recall there will be the same entire row weights in the different kernels. So the computations with the same activations will be recomputed. So we propose the entire row result reuse method to tackle this problem. In our architecture, the activation will be processed row by row. For example, in a 3 times 3 count process, one activation row will be counted with 3 row weight. So their results will be stored in one memory, and the second activation multiplied count with the 3 row weights will be stored in the memory 1. And when the third input activation row are generated, they will be added with the activations in the memory 0 and the memory 1, and in this way, the complete activations over count windows can be generated. And when the fourth row activation is input. Their results will be stored in the memory 0 because the first activation rows will not be used again. So in this way, the memories and the activation inner the memories will be reduced. It's also similar to the SCN. And the third, we propose a sub-area-based filter mapping method. We do not use a single P as the basic computer unit. We use a sub-area as the basic computer unit in the transfer filter-based algorithms. So the input activation will be broadcasted in the basic computer unit. This can greatly reduce the complexity, the control logic, and the power and the error consumption can be reduced too. Let's look at our experimental results. We first compare with the baseline architecture of the arrays. We use the same technology, the same voltage, and the same frequency. So we use more PEs, but the TFE require less memory, area, and power than the arrays. And let's look at the area and power breakdown. As the computations are reduced significantly and the data reusability is so high, so the overhead comes to the memory axis, just as the results should. And we look at these two pictures. The TFE can output areas in 4 benchmarks, not only on the cover layers, but also on the overall networks. And we also compared with the other related works. First, we compared with the compression-based methods. We can see that the higher parameter reduction can be achieved in this method. However, not that high speed up can be achieved because of irregular computation. And when compared with the computation reduction-based works, we not only can reduce more parameters, but also can achieve a higher speed up than these methods. Finally, please let me make a conclusion. In this work, we propose an energy-efficient and high-speed engine for CNN compression and acceleration. This is the first systematic solution that explores transfer filter-based algorithms, and the transfer filter algorithms can be used for mainstream networks, namely our architecture, our engine can support mainstream networks. In our architecture, two hardware-friendly techniques are proposed in the TFE to reduce the redundant computations. And we also designed an efficient TFE hardware architecture to support the above process efficiently with a new or lower mapping method named SAFM. That's all. Thank you. Thanks for your listening.